In the previous lectures, we discussed about the proton NMR and C13 NMR. Now we will discuss about the F19 and P31. Both of them have a spin of half. As far as F19 is concerned, it has got 100% abundance. That is, the interesting thing is, fluorine has no isotope at all. Everything is only F19. And the chemical shift ranges from minus 300 to 400 ppm. So totally a range of about 700 ppm. The reference compound which we use here is, we said that for proton and C13 NMR, we use tetramethylsilane as the reference material, standard material. Here, the reference material is CFCl3 and we assign 0 ppm value to that. And some of the properties of F19 are, the magnetogyric ratio is 251 mega radians per Tesla per second compared to proton, which is slightly excess fluorine. And for C13, it is only 67.2828. Okay, now fluorine couples with nuclei having spin. I will mention about the fluorine coupling. The coupling constant J between fluorine nuclei cover a wide range. Geminal fluorine the coupling constant value is about 43 to 370 Hz, depending upon the other groups which are present there. That means what I mean to say is, I have fluorine like this. They coupled with a J value of ranging from 43 to 370 Hz. And vicinal (0 to 39). Cis fluorine (0 to 58) and a trans 106 to 148. So trans coupling is stronger. Another special case in the case of fluorine is, it has a long range coupling. Even the intervening bonds are 5. This fluorine can couple with that fluorine. Such a coupling is called a long range coupling or through space coupling. And the coupling constant for this is about 0 to 18 Hz. Coupling between proton and fluorine is also strong. Coupling between fluorine and proton is also strong. For geminal, the value is 42 to 80 Hz. For vicinal, the value is 12 to 29 Hz. And cis HF coupling has a value of 0 to 22 Hz. And a trans has a value of 11 to 52 heads. Fluorine, when attached to benzene ring, also couples with the protons in the benzene ring. And the JHF value for our ortho derivative ranges from 7.4 to 11.8. For meta, it ranges from 4.3 to 8. And for para, it ranges from 0.2 to 2.7. Now let us look into some of the F19 spectra of some few compounds. Let us say I have a compound like this. One fluoro, one bromo, ethane is the compound. How will the proton NMR look like? And how will the fluorine NMR look like? We'll discuss about that. The proton NMR, this proton will couple with these three protons. So the CH signal will be a quartet. This is the CH signal. And this CH3 will be coupled by this proton. So this will be a doublet. Actually speaking, the intensity ratio also should be mentioned. For these three protons, the intensity will be larger. And for these two protons, the one proton intensity will be less. I have not drawn according to size. This should be 1:3 ratio. Now, this is the compound. I said this is the signal for CH and this is the signal for CH3. Now, this signal will be split by fluorine also. This is the splitting by hydrogen. Fluorine has a spin of half, I said. So splitting +1 is a splitting. So each line will be split into two. So splitting by F will be this will be the CH splitting due to fluorine. A quartet become an octet. And this will be a quartet. This will be a quartet. So that's about the spectrum of one fluoro, one bromo, ethane. Now let me sketch the fluorine NMR spectrum of this compound. This is the proton NMR, splitting by the fluorine. Let me talk about the fluorine NMR of this compound. There is only one fluorine. So you will get a signal. It will be split by the geminal hydrogen into two. And it will be further split by these methyl hydrogens, each into a quartet. So this will be the F19 spectrum of 1-fluoro, 1-bromo ethane. I have sketched both the proton NMR as well as the F19 NMR. One more interesting application is we have a compound bromine pentafluoride. We may suggest a trigonal bipyramid structure for this normally. But the NMR says that, the fluorine NMR says that it is not a trigonal bipyramid, it is a square pyramidal structure. The F19 NMR of this compound shows two peaks, a doublet and a quintet. The fluorine signals are, that is, I said the structure is this is the structure. Square pyramidal is the structure. Had it been trigonal bipyramid, 3 fluorines will give a signal and 2 other will give a signal. So the intensity ratio should be 2:3. I said the intensity ratio is 4:1. So 4 fluorines belong to one type and 1 fluorine belongs to other type. The more intense signal is split into a doublet and the less intense signal is split into a quintet. So another interesting example is that the structure of CLF3. The fluorine NMR of this compound doesn't show a single line indicating that all the 3 fluorines are equivalent. Instead, you get 2 lines of intensity 1:2. That means 2 fluorines are equivalent and the third one is different from the other. Based on this, they proposed a T-shaped structure for this compound. 2 longer fluorine bonds and 1 shorter CLF bond. So the spectrum looks like this. You get a doublet and a triplet. This is the signal for these 2 fluorine atoms, which is split into a doublet. And this is the signal for this fluorine atom, which is split into a triplet. You will note that these 2 fluorines are at a downfield and this fluorine is at a upfield. Well, the reason is very simple. Namely, these fluorine atoms, these 2 fluorine atoms attract the electrons towards this fluorine, so they absorb at a downfield. And this single fluorine, which is shielded, absorbs at a high field. So this is a very interesting application of fluorine NMR. Now let's move on to P31 NMR. This also has a spin-off plus off. It is also %100 abundance, spin is equal to half, and the gyromagnetic ratio is 108.41 into 10 power 6. It's the gyromagnetic ratio, and it is 2.5 times smaller than that of a proton. And phosphorus coupled to hydrogen, and a point to mention here is the coupling constant JPH increases with decreasing electron density on phosphorus. Just to compare, let us say I have a phosphonium compound pH4 plus, I have pH3, and I have pH2 minus. And the JPH values are, it is 547 for this, 189 for this, and 139 for this. Compared to pH3, the pH2 minus has more electron density on phosphorus, therefore the J value is small. Compared to pH3, the phosphonium ion has a J value of 547, namely the electron density is low. So that's about the JPH values. So it can couple with the proton. Now, you must be familiar that phosphorus has a H3PO3. This is the structure H, OH, OH. Of course, we have an oxygen here. This is the structure of H3PO3. Okay. Right. Now, I am sketching the phosphorus NMR signal for this compound. These are ionizable, or it will undergo fast exchange also. So this will not split the phosphorus signal, only this will split the phosphorus signal. So I will get a doublet for this. I will get a doublet for this. This is the JPH. And hypophosphorus acid. Hypophosphorus acid. H3PO2. The structure of this compound is the structure of this compound. So this phosphorus will be split by these two hydrogens. This ionizable hydrogen, so it will not split it. It will undergo fast exchange also. So we get a triplet for this. So using phosphorus NMR, we are able to distinguish between the hypophosphorus and the phosphorus acids. If we talk about the phosphoric acid, I need not mention that. You are very familiar with that. This is the structure of phosphoric acid. You get a signal for phosphorus with no splitting at all. So you get a singlet because all the three hydrogens are ionizable or can undergo fast exchange in the presence of a drop of acid. So the phosphorus gives just a singlet. So you can distinguish between phosphorus, phosphoric, and hypophosphorus. All the three can be distinguished using the phosphorus NMR. One more interesting example is that we have a compound of formula P4S3. S is having I is equal to 0 because there are 16 protons and 16 neutrons, even number of protons and neutrons. So I is equal to 0, it will not cause any splitting at all. Whether all these four phosphorus are equivalent or not. If you record the spectrum, phosphorus spectrum of this compound, you get two signals. 3 phosphorus belonging to one type and other one is unique. And based on the phosphorus NMR, the structure proposed is this. Namely, you have these 3 phosphorus are equivalent phosphorus. And each phosphorus, and you have the 4th phosphorus is here. Each phosphorus is bound to the other one through a sulfur bridge. You will note that as far as these 3 phosphorus are concerned, each phosphorus is attached to 2 phosphorus and 1 sulfur. You can verify each phosphorus is attached to 2 phosphor and a sulfur. 2 phosphorus and a sulfur. And this phosphorus is attached to 3 sulfur atoms. So this is the structure for P4S3. So this is unique. This will give a separate signal, and these 3 are equivalent, magnetically equivalent. So they give a signal. So the structure of this compound could be established. So using the fluorine NMR and the phosphorus NMR, we are able to establish the structure of a number of molecules. I have just touched the surface. I have given a few examples. You can refer to any textbook and find innumerable examples. Finally, a note about what is called FTMR. Fourier transform NMR. What is this Fourier transformation? Normally what we do is, in any spectroscopy, we scan through frequencies. One by one, we send frequencies and find whether it is absorbed or not. Whereas in the Fourier transformation, we give all the frequencies together as a pulse. Then you analyze the radiation given out. We call it free induction decay, FID. That is plotted as intensity versus time. That's known as the time domain. Using a mathematical procedure, we convert this into the frequency domain. Intensity versus time is converted into intensity versus frequency. Such a technique is called an FTMR technique. There is FTIR also. So what you have to do is take the sample, give all the radio frequencies as a single pulse, and some will be absorbed, some will not be absorbed, and what is given out, you get a plot of the intensity versus time. That's what I told you as a time domain. Using the Fourier transformation, which is a mathematical procedure, convert this into frequency domain, intensity versus frequency, and find out where are the signals obtained for different phosphorus atoms. As I told you, FTIR is also there. So this is the time-saving procedure. You need not spend a lot of time as you record for NMR, normal NMR. This is time-saving procedure. Okay. I said that this is time. You get a signal like this. Time versus intensity. Using Fourier transformation, we convert this into intensity versus frequency. Intensity versus frequency. Then you get signals like this. You find out which frequencies are absorbed and propose a structure for the compound. Basic principle of FTMR. The conventional NMR is not so sensitive. Suppose the quantity of the sample is in the order of microgram. It is very difficult to obtain a good spectra in conventional NMR. And time consuming is also more. You have to scan through all the radio frequency. It takes a longer time to record a scan. So these are the drawbacks of the conventional NMR. Whereas the features of FTMR, okay, these are the basic features in the FTMR. Namely, you stimulate all the transitions simultaneously by irradiating the sample with a pulse of radio frequencies on the proton range or whatever spectrum you are recording, and relaxation takes place by emission of the radiation or by what is known as free induction decay, and what you get is a time domain spectrum. As I told you earlier, intensity versus time. And the Fourier transform, the mathematical procedure, converts that time domain into frequency domain. So you get a very good NMR spectrum in a very short time, and very much of clarity is there. So this is the technique used in the FTMR.